Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at section 1.4. This is the delta function, and I want to derive it using a little, maybe a different style, but this is what our author does, and it's quite clever. So let's do this. Let's take a look at, I'm going to introduce a new function that's going to lead us to a function we just studied, the Heaviside function. We're going to use that to study the delta function. So here's how we're going to do this. The first function I want to look at is called the ramp. Oh, let me get a better color here. How about this one? So let's take a look at this. So up to 0, it's 0. And then at 0, it takes off and it becomes t. So it looks like that. So this is t. Well, this is called the ramp function. And so the ramp function, using an r to denote this, r of t, is it's 0 when t is less than 0, and it's t when t is greater than or equal to 0. That is our ramp function. Now, let's do something more. Now we can do this both visually and we can do it algebraically. We'll try both. Let's take the derivative with respect to t of the ramp function. Well, the derivative of 0, we know that's just 0. And we know that the derivative of t, that is 1. Well, let's take a look at what happens here. So again, this is for t less than 0. And this is for t greater than or equal to 0. Now I'm going to draw this picture. And I should maybe do this in blue too. Draw this. And then we're going to label this. And now, wait a minute. So this is the blue graph. Well, this says we're at 0 up until we get to 0. And then when we get to 0, we're not at 0 anymore. We jump up here to 1. We jump up to 1. Well, we've seen this before. That is our step function, and which is named after Oliver Heaviside, so it's also the Heaviside function h of t. Wow, and we can see this visually, that the slope of the line t is always 1. It just becomes a constant. Now, let's try this again. Let's do this. So now, let's take the derivative. Let's take the derivative with respect to t of the Heaviside function. Well, let's take a look. We'll do this both again visually and graphically. Now, when I take the derivative of 0, I'm at 0. And when I take the derivative of 1, well, I'm at 0 there. But now let's do this in another color. How about this kind of pretty pinkish color? So the derivative of 0, that's 0, creates the graph of 0. The derivative of 1, that is 0. Now, you can see that the problem when you take a derivative is if you have a discontinuity. Because essentially, this t function, this graph, if we get closer and closer to 1 from the right-hand side, it's getting closer to 1. From the left-hand side, it's getting closer to 0. And what we do is, so really it's undefined here. When it's something that's undefined, we think of it as being asymptotic. So I'm going to just represent this strange gap, and what we do is we represent it with just a vertical line that's just racing off to infinity of sorts. You could have it going to negative infinity, but since we're going from 0 upwards, we'll just make it vertical. That's the standard. So what we do is we say that the derivative is 0 or it's infinite. And it's infinite when t is 0, and it's 0 otherwise. This is called the delta function. Sometimes you'll hear it called the Dirac Delta function. But it's called the delta function. And what does it do? The delta function has the effect of making an impulse. like if you were to hit a golf ball, or if you were to maybe fire a gun. There's just one massive explosion in an infinitely short period of time. I mean, maybe it's measurable, but it's so insignificant that it just happens at instantaneous point in time. Now, the question though is, in solving our differential equations, we end up taking an integral. Derivatives are messy. Integrals are actually quite robust. So let's see if we can figure out how I can find out what is the integral of the delta function. And if you notice that this problem, really, our pink lines here, they start at negative infinity. And they go all the way out to infinity. Well, it's because of the fundamental theorem of calculus that we can easily solve this. Otherwise, we have to be a little bit more creative, and there's another approach to this, but I think this is probably the most elegant route that our author takes. So let's understand this. Well, remember that the delta function is just the integral from minus infinity to infinity of the derivative with respect to t of the heaviside function h of t dt. Well, now we know this. If I take the antiderivative of the h of t, well, here's what we get. This is kind of an interesting idea. We'll call it h of, now this is going to be weird, the h of a positive number, we'll put it in infinity, minus h of some negative number, we'll call it negative infinity. Well, I know that's not normal notation, but look at what this means. What is h, the heaviside function, if it's positive value? Well, it's 1. And what is h if there's a negative value in there? It's 0. So no, in other words, the delta function, the integral from negative infinity to positive infinity of the delta function is just 1. And that makes it so slick to use because say you wanted an instantaneous impulse of 10, like you're really going to swat that golf ball hard. Well, all you have to do to change your integral is just multiply it by 10, and you'll be exactly where your optimism takes you. All right, so then that brings up our next question. That is, how do we find the solution to our differential equations? Well, a few things happen. The first one is we need some definition. So let's do this. If I have the integral from minus infinity to infinity of the delta function, call it of s, times some function, we'll call it capital F of s ds. Now, this is what we think about. The delta function, remember, only at that instantaneous point in time does it make a contribution. At that point, it just becomes 1 for that little like flash of light. Well, the delta function becomes 1 at 0. The rest of the time, it's just the integral is 1 at 0. So the rest of the time, it's just 0. So essentially, what we're only going to see is we're just going to be evaluating f at that one instant in time, f of 0. And these are more kind of an intuitive solutions. So if I want another one, if I have the delta function of t, let's use t here, t minus t, f of t, dt. Well, this is the same idea, except that now the flash doesn't come at 0, it comes at capital T. So then f is evaluated at capital T. And that is the shift of the delta function. Maybe you wanted it to happen later on in time. All right, so the question then is, how do we solve this? Well, let's try this. Let's recall this. So, you know what? I think I'm just going to go to a new page. Well, we'll get started, and then we'll go on as we need to. So remember, we're going to solve. So we're going to solve the differential equation y prime equals ay plus, and now we're going to say q of t is, we're going to just do this delta of t minus capital T. You could just do t, but I think there's more to be learned from this final solution. Okay, well, we start out with our integrating factor. So y prime minus ay equals delta of t minus t. And then we said our integrating factor would be, our integrating factor m in this case is e to the minus at. So we multiply by that. So then we're going to take the integral from y of 0 to y of t times the derivative with respect to t of e to the minus at. That's what the integrating factor does. It just says we just get to use that value times the function y and dt. Now, and if you're a little confused on that step, we do review that in an earlier video. And then we're going to take the integral on the right-hand side from 0 to t. And this is going to be e to the minus a, we'll use s here, as delta of s minus capital T ds. Okay, on the left-hand side, this becomes e to the minus at y of t minus y of 0. Now on the right hand side, this is where this problem, I'm going to leave it here. We're going to work on that on our next page. Integral of e minus as delta of s minus t ds. So let's do this. Let's take, and we're going to take this piece with us. I'm going to copy it. And then let's go to a new screen. Let's turn our old one off. Let's come over to here. We're going to go paste, clipboard, and let's just put this up here in our corner, and that's where we're going to start. Okay, there we go. So I have, let's start cleaning things up. This is e to the minus at y of t equals y of 0. Plus the integral from 0 to t, e to the minus as delta of s minus t ds. And then finally, we multiply everything out by the reciprocal of e to the minus at, which is e to the positive at. So this is going to give us a y of t equals y of 0 times e to the at plus e to the at, the integral from 0 to t, e to the minus as delta s minus t ds. Now this is where we can start evaluating using the tool that we had just learned. Y of 0 e to the at plus e to the at. Now remember, this e to the as, this is our, we call that our function f of s. So what we said is that becomes an instantaneous moment that function has value. The function has value at capital T, and then it's 0 the rest of the time. So what we get is e to the at times e to the minus a capital T. Okay, one last step here, y of 0, e to the at plus, and then let's factor out the a, and we're going to write this as e raised to the a times t minus capital T. Now, we need to think about our solution a little bit more, and I'll show you why. Because think about what just happened here. So initially, let's do this. Our function was y of t equals, and what happened is up until the point, so here's our solution. Oops, I'm going to fix that, make a nice vertical line. So what happened is maybe this is their point capital T. Is our solution, maybe it had some exponential, could be decay. Maybe it was starting to go back down. Maybe it was coming back down here. Well, then at capital T, delta kicks in, and maybe it jumps it back up again. Maybe it jumps it right up to there. And then this comes back down. Maybe it decays again. And so here's our initial condition. This is where the problem starts. It's decaying or growing up until T, and then it gets a boost, and then it repeats itself now based on the two of these pieces combined. So really there's two parts. Initially, there's just this piece, and let's write it this way. Y of t equals, I should probably put in here, let's write it this way. I'll write it as y of, just recopying, equals y of 0, e to the at plus e raised to the at minus capital T. Well, this is just your null solution, and this is your particular solution. Because remember, nothing happened at t of 0, so there's no contribution from our integral into the null solution. And so y of t equals, well, initially it's just y null, and it gets 0 from my particular solution. And this is for t less than capital T. Okay. Then it gets this boost, and it becomes y null plus y particular, and that is when your time is greater than or equal to t. So, oh, this is clever. Look at this. Look at what we just did. Notice that the y particular, when t was less than t, is 0. Then the y particular becomes 1 y particular once t is greater than or equal to t. In other words, we have to turn t on. How do we do that? We do that with this little piece. If I had blue and I just looked at this picture right there, maybe even more refined down to right there, the 0 and the 1, that's the Heaviside function. In other words, in order to make this problem work, our y particular needs a Heaviside addition. So to make this problem work the way you would like it to, we would write our final solution. Y of t is the null solution, e to the at, plus our particular solution, e to the at minus capital T, times the Heaviside function that turns it on at capital T. And that would be the solution to the instantaneous input and that is contributed by the delta function. Now, before we close, a few little comments are in order, and that is this. The delta function is not a function in the normal sense. And when I say that, what do I mean? I mean because a function by itself means that it's a vertical line only crosses it once. And obviously the delta function has an entire vertical line in the function. So that's not normal. Also, the way we interpret the derivative of the Heaviside function at time is 0 is what we call that is the derivative of h. When we write it, the result as delta, as the delta function, you don't need to, no, sure, I'll write it of t. This is called a generalized derivative. It's a big deal. It's called a generalized derivative. And we're not going to worry about this. Here's the amazing thing about the delta function is that it does work, even though it just does not behave the way we like it to. It kind of goes against your best spidey sense, but that's okay. I want to show you, though, really briefly, one more idea that might put your mind a little bit more at ease. And I'm not going to run through the whole idea, but one way to define the delta function is with some function, we'll call it d sub t. And what d sub t is, it's 1 over t. This is for when t is less than or equal to capital T or greater than or equal to 0, and it's 0 otherwise. Well, if something is of height dt, so between 0 and t it has a height here of 1 over t, well, then maybe then this would be capital T. So look at this. Well, then if you said the integral from negative infinity to infinity of, oops, let me write this way, of this function, we're calling it d sub t of t dt, well, that's just going to equal 1. Well, here's what gets interesting. If we take, but what if happens then if t starts to get smaller? So, well, notice that the integral of this is just going to be 1. So as capital T starts moving to the left, maybe t goes here, well, then 1 over t is going to move up. Whoops. There. So this is my new 1 over t. Well, the question then becomes, well, what happens then as t goes to 0? Right back here. Then that means that 1 over t just becomes infinite. And so another way of looking at this is that it's the integral from negative infinity of the limit as capital T tends to 0 of d sub capital T of t dt, and that this is another way of looking at the delta function. So that would be another way. It's easy to get caught up in confusion about the delta function, but it works. But we're going to just use it as a definitional operation. And that it allows us to do is to create an instantaneous impulse at some point in time being represented by capital T. So and I point this out because I believe that this function was first invented by a physicist to show impulse, and it created all sorts of mental grievances for mathematicians over the years, because it just is not really a function by the way that mathematicians have defined a function, yet it works perfectly. And we're going to just run with the fact that it works so well. That's the delta function, the instantaneous impulse at a moment in time. I hope that helps, and thanks for watching.